The year is 1961. The setting is a sterile, high-ceilinged conference room within the grim brutalist architecture of the Soviet Admiralty. Professor Georgy Logvinovich stands alone at the front of the room. He is facing a row of Soviet Navy admirals, men whose chests are heavy with metals and whose patience is notoriously thin. The Cold War is entering its most dangerous freeze. The Cuban Missile Crisis is on the horizon, and the underwater arms race is dominated by nuclear propulsion and silent stalking. But Logvinovich is not there to talk about silence. He is there to propose a weapon that screams. He outlines a torpedo concept that defies every convention of naval warfare. He tells the admirals that he can build a weapon capable of traveling at 200 knots. That is roughly 370 kilometers per hour. To put that in perspective, the fastest torpedoes currently in the Soviet arsenal, or the American arsenal, for that matter, top out at 50 knots. Logvinovich is proposing a weapon that is not just faster, it is 4 times faster than anything afloat. It is a leap in performance, so vast it sounds less like engineering and more like science fiction. The admirals lean forward, their faces a mix of curiosity and deep skepticism. They know the ocean. They know the crushing density of water. At sea level, air has a density of about 1.2 kilograms per cubic meter. Water is 800 times denser. Trying to push a solid object through water at 200 knots is, physically speaking, like trying to fire a bullet through a wall of concrete. The drag forces involved are exponential. As you double your speed, the drag doesn't just double, it quadruples. To go 4 times faster, you don't need 4 times the power. You need nearly 64 times the power. It is a wall of physics that no engine in 1961 can breach. Logvinovich knows this. He points to his equations on the chalkboard. His solution is not to overpower the water, but to remove it from the equation entirely. We will not swim through the water, he explains. We will fly through a bubble. This is the concept of supercavitation. The idea is to wrap the entire weapon in a self-generated envelope of gas. If the torpedo is inside a bubble, the hull is no longer touching the dense, dragging water. It is touching gas, arguably water vapor or injected air. The friction drops from that of a submarine hull to that of an aircraft fuselage. In theory, if you can eliminate the water contact, you eliminate the hydrodynamic drag. The mathematics are elegant. They are beautiful. Logvinovich demonstrates that if gas is vented continuously from the nose of the weapon, the water molecules simply cannot accelerate fast enough to close around the high-speed object. They get pushed aside, and before the water pressure can collapse the fluid back against the hull, the torpedo has already moved past. The weapon rides inside a stable cavity, a ghost in the machine of hydrodynamics. But the admirals are not mathematicians. They are pragmatic men responsible for the defense of the Soviet Union. They point out the immediate, glaring problem. No engineer, Soviet or American, has ever sustained supercavitation beyond a laboratory flash tank. In a flash tank, a tiny test slug, centimeters long, punctures a thin film of water for a fraction of a second. High-speed cameras capture the bubble for a millisecond, and then it is over. Logvinovich is proposing to take a phenomenon that lasts milliseconds and sustain it for minutes. He wants to scale it from a centimeter-long slug to a 7-meter-long weapon of war. The gap, one admiral remarks, between chalkboard equations and a deployable weapon is vast. They are right to be worried. Conventional torpedoes of the early 1960s are hitting a hard ceiling. When a propeller spins too fast underwater, the pressure on the back of the blades drops so low that the water literally boils at room temperature. This creates bubbles, cavitation. When these bubbles collapse, they do so with violent force, pitting the metal and creating noise. This is propeller cavitation, and it is the enemy of speed. It limits conventional weapons to about 50 knots. Even the most advanced electric torpedoes in the Soviet fleet cannot break this barrier without burning through their batteries in seconds. The drag is simply too high. Logvinovich is promising to leap past that ceiling entirely. He argues that if the bubble can be generated and sustained, the drag will vanish. The torpedo won't need massive batteries because it won't be fighting the water. The strategic implications are terrifyingly attractive. At 200 knots, a torpedo could cross a 7-kilometer engagement zone in under 2 minutes. A U.S. carrier group would detect the launch. But before the captain could even order the rudder hard over, before the destroyers could deploy countermeasures, the weapon would impact. It would be faster than the reaction time of the target. The admirals confer. The Soviet Navy is engaged in a budget war as fierce as the Cold War itself. Submarine construction, nuclear propulsion programs, and ballistic missiles are all competing for the same rubles. They cannot afford to invest in theoretical hydrodynamics indefinitely. They make a decision. They approve the research program, but they attach a condition that hangs over the team like a guillotine blade. Logvinovich receives laboratory space, a small staff, and access to Navy test facilities. But he is given a strict timeline. Without a working prototype, not a model, not a math proof, but a working system, funding will be cut within 5 years. The clock starts ticking immediately. The team has 5 years to solve a problem that has baffled physicists for decades. How do you keep a bubble alive when the ocean is trying to crush it? Early experiments at the Navy's Hydrodynamics lab begin to show just how difficult this will be. They start with propellers. The logic is simple. Spin a propeller fast enough, and it creates bubbles. Can we spin it fast enough to create a bubble that swallows the whole ship? The answer is a resounding no. The spinning propeller creates localized cavitation bubbles on the blade tips, violent and chaotic. But those bubbles collapse within milliseconds. They do not extend forward. The torpedo's nose and midsection remain in full, grinding contact with the water. The drag remains. The engineers run the numbers. To sustain a bubble that covers a 7-meter hull for a 7-kilometer run, they would need to vent hundreds of liters of gas per second. No propeller wake can produce that volume. The physics of the propeller are a dead end. The propulsion team sits in the lab, surrounded by failed models and reams of data. They come to a stark conclusion. If they are going to wrap a torpedo in gas, they cannot rely on the water to generate it. They need to bring the gas with them. They need a fundamentally different gas source, one that can scream out volume at a rate never before attempted underwater. The era of the propeller is over. The era of the gas-vented supercavitating projectile has begun, and with it, a journey into engineering darkness. The program moves. To maintain absolute secrecy, the team leaves the familiar naval bases and relocates to the heart of Central Asia. Their new home is Lake Issyk-Kul in Kyrgyzstan. This is not a standard naval proving ground. Issyk-Kul is a geological marvel. It is a high-altitude lake surrounded by the towering, snow-capped peaks of the Tian Shan Mountains. These mountains serve a dual purpose. They create a stunning backdrop, and more importantly, they block the line of sight for foreign reconnaissance satellites. The lake is vast, deep, reaching 668 meters, and isolated. It is the perfect place to hide a weapon that doesn't exist yet. But the isolation brings danger. The lake is landlocked. There are no submarine rescue ships nearby, no open ocean to drift in. Recovery operations require divers and small surface vessels operating in a confined envelope. The engineers map out a narrow test corridor along the deepest section of the lake. They calculate the margins. At 200 knots, the weapon covers ground so quickly that even a 2-degree deviation in trajectory would put the prototype outside the safe zone within 30 seconds. If it veers left, it hits the shoreline. If it veers right, it drives into the lake bed. Either result destroys the prototype and potentially kills the recovery crews waiting on the surface. The test range offers secrecy, but it offers no margin for error. The team begins with the most obvious solution for gas generation: compressed air. It seems logical. You fill the torpedo with high-pressure air tanks, and as it moves, you blow that air out through ports in the hull to create the bubble. The initial tests in the clear waters of Issyk-Kul look promising. At low speeds, the air vents, the bubble forms cleanly, and the drag drops exactly as Logvinovich predicted. The team watches the data streams, drag coefficients plummeting. For a moment, it looks like the solution is at hand. Then, the reality of volume sets in. The onboard air tanks exhaust themselves in seconds. To maintain the bubble, the flow of air must be massive and continuous. As soon as the tanks run dry, the gas flow stops. The bubble, starved of pressure, is instantly crushed by the surrounding water. The torpedo, suddenly exposed to the full friction of the lake, hits a water wall. It decelerates violently, slowing to conventional speeds. The engineers sit down to do the volume calculations again. For a 7-kilometer run, the requirement set by the admirals, the torpedo would need to carry tanks larger than the weapon itself. The energy density of compressed air is simply too low. To store enough gas to feed the bubble, the torpedo would become a tanker. Heavy and slow. It is an engineering dead end. The realization hits the propulsion team hard. They don't just need gas. They need high-energy gas. They need a system that generates gas as a byproduct of propulsion, not as a consumable payload they have to carry. There is only one engine capable of producing that kind of volume, a solid-fuel rocket motor. A rocket motor doesn't just push, it burns. It turns solid fuel into massive amounts of high-pressure exhaust gas. It solves the volume problem instantly, but it creates a new, terrifying problem: geometry. In a conventional rocket, the motor is at the back. The fire comes out the tail, pushing the weapon forward. But for Logvinovich's team, this is useless. If they vent the exhaust out the back, the gas flows away from the torpedo. It leaves the nose, the part of the weapon hitting the water first, completely exposed. The nose is the stagnation point, the place where water pressure is highest. If the nose is touching water, the drag is still there. The weapon might go faster because of the rocket thrust, but it won't supercavitate. It will just be a fast, loud rock. The propulsion team stares at the blueprints. They face an impossible geometry problem. The motor must generate enough gas to wrap the entire hull, but that gas has to be at the nose. If they mount the rocket at the back, the gas is in the wrong place. If they mount the rocket at the front, the weight balance is destroyed, and the exhaust would have to flow back over the control surfaces, melting them. They need the gas to reach the nose without melting the structure of the torpedo, and without the flow collapsing under the immense back pressure of the water hitting the front of the weapon. The breakthrough comes in a single afternoon of feverish sketching. The propulsion team proposes an inverse configuration. It is a design that turns conventional rocketry on its head. They decide to mount the solid-fuel rocket motor amidships in the middle of the torpedo. But instead of just shooting the exhaust out the back, they will duct a portion of that superheated gas forward. Imagine the engineering audacity. They plan to take exhaust gas that is 2,000 degrees Celsius and channel it through internal tubes running the length of the forward section, right up to the nose cone. They will drill a ring of holes, venting ports, into the nose itself. The concept is to use the rocket exhaust to punch a hole in the water. The gas will exit the nose, nucleate a cavity right at the stagnation point, and then flow back over the body of the weapon. The torpedo will effectively fly inside its own exhaust plume. It is brilliant, it is elegant, and it is a thermal nightmare. The team sketches the concept, but the materials engineers look at it with horror. They are now being asked to build a nose cone that must survive two opposing forces simultaneously. On the outside, it faces the crushing impact pressure of water at 200 knots. On the inside, it faces the melting heat of rocket exhaust at 2,000 degrees, and there is no room for active cooling systems, no pumps, no radiators. Building the nose becomes the critical path. The entire program, the 15 years of funding, the reputation of Logvinovich, now rests on a piece of material no larger than a dinner plate. Wind tunnel water tests are scheduled. They build a scaled model fitted with a gas injector. They mount it in the test section and accelerate the water flow to simulate high-speed conditions. The cameras are rolling. The gas vents. Within milliseconds, a hemispherical cavity forms at the nose. It is perfect. The bubble grows aft, wrapping the model's midsection, then the tail. The sensors register a drop in drag of 90%. 90%. The model is gliding. High-speed cameras capture the stability of the bubble. It holds its shape across the entire length of the test section. It doesn't collapse. It doesn't separate. It pulsates slightly, a living skin of gas. But it holds. The propulsion team has proven the concept at scale. The physics works. The geometry works. Now, they have to build the real thing. They have to find a material that can sit in a blast furnace while smashing into a brick wall. The search for the nose cone material is not a simple metallurgical survey, it is a battle against thermodynamics. The nose cone must endure exhaust temperatures exceeding 2,000 degrees Celsius. Steel would soften and deform. Titanium would burn. The engineers realize that no metal can survive this environment without cooling. They turn to the space race for inspiration. They select ablative ceramics. Ablation is a violent form of protection. It is the same principle used on the heat shields of spacecraft re-entering the atmosphere. The material is designed to die. As the heat hits it, the outer layers of the ceramic vaporize. As they turn to gas, they carry the heat away from the structure. The material sacrifices itself to save the ship. But in the underwater environment, the trade-off is agonizingly tight. It's a game of millimeters. If the ceramic ablates too quickly, the nose cone will lose its shape. If the shape changes, the gas flow becomes turbulent. The bubble will collapse. If the bubble collapses at 200 knots, the water will slam into the hull with the force of a train wreck, shattering the lightweight airframe instantly. However, if the ceramic is too thick, it adds massive weight to the nose. This shifts the center of gravity forward, making the torpedo unstable. It would dive into the mud moments after launch. The materials team sets to work. They machine a series of prototype nose cones, experimenting with different ceramic composites, different thicknesses, different bonding agents. They test them in static rocket firings on the shore of Lake Issyk-Kul. They bolt the nose cones to a test stand and fire the rocket, blasting them with fire for minutes at a time. They measure the erosion rates with micrometers, looking for the perfect balance between survival and weight. Finally, they have a candidate. It is 1972. 15 years have passed since Logvinovich stood before the admirals. The 5-year deadline has been extended, again and again, based on incremental progress. But patience is at an end. This is the moment. The first full-scale prototype is loaded onto a launch sled at the edge of the lake. The weapon is imposing. It is 7 meters long, 533 millimeters in diameter, the standard dimensions of a Soviet torpedo tube. It weighs just under 2 tons. It looks like a standard torpedo, except for the nose, which is capped with the strange, dull-finish ceramic ring perforated with exhaust vents. The rocket motor is loaded with solid fuel. The engineers inspect the nose cone one last time, looking for hairline fractures. If the nose fails during the burn, 15 years of research evaporates. Recovery divers will find only debris on the lake bed. The range is cleared. The countdown begins. The rocket ignites. Inside the combustion chamber, solid fuel burns at 2,000 degrees. A torrent of high-pressure gas screams through the internal ducts. It hits the back of the nose cone and is forced out through the ring of perforations. The gas exits the nose at supersonic speeds, directly into the water. The ablative ceramic begins to glow orange as the temperature peaks. But it holds. The gas flow reaches several hundred liters per second, a volume far beyond what any compressed air system could ever dream of. The stagnation point, the place where water pressure is trying to crush the weapon, effectively disappears. It becomes the birthplace of the bubble. The exhaust hits the water and instantly vaporizes a hemispherical cavity. The water pressure pushes back, trying to close the hole, but the relentless stream of rocket exhaust holds it open. The cavity grows. It expands aft, racing along the hull. The interface between gas and water forms a thin, turbulent boundary layer. Inside the control bunker, telemetry shows the skin friction dropping to near zero. The hull is no longer touching water. It is flying through a self-generated tunnel of gas. Only the nose cone remains in direct contact with the interface, a thin film of gas and vapor where the exhaust first meets the lake. Hydrodynamic drag, which should be skyrocketing, has been almost eliminated. The rocket motor accelerates the weapon. It pushes against negligible resistance. The speed climbs. 100 knots. 150. This is the moment Logvinovich dreamed of. Sustained supercavitation. The rocket accelerates the torpedo to 200 knots in under 3 seconds. The G-force is immense. The weapon crosses the first kilometer marker in a blur. For the observers, it is a blur of physics and violence. For the weapon, it is a smooth, frictionless glide. It crosses the 7-kilometer test range in less than 2 minutes. To put this in perspective, a conventional 50-knot torpedo fired at the same time would still be struggling near the start line. It would take nearly 8 minutes to cover the same distance. In a combat scenario, that 8 minutes gives an aircraft carrier time to turn, time to launch decoys, time to deploy screening ships. But the Shkval, the Squall, removes that time. It eliminates the decision window. By the time the target realizes it is under attack, the weapon is already there. The prototype reaches the end of the test corridor. The rocket burns out. The gas flow stops. The bubble collapses. The water grabs the hull, and the weapon coasts to a halt. Recovery divers locate it by sonar. They attach flotation bags and winch it to the surface. As it breaks the water, engineers crowd the deck of the recovery vessel. They ignore the hull. They look straight at the nose. It is scorched black. There is deep heat scoring where the ceramic eroded, but the shape is intact. There is no structural failure. The geometry held. 15 years of theory, 5 years of scaled testing, and 3 years of full-scale development have produced a weapon that actually works. The Soviet Union has broken the speed limit of the ocean. The engineering victory is absolute. But as the champagne corks pop at Lake Issyk-Kul, the tactical officers of the Soviet Navy begin to review the data. They look past the speed and focus on the side effects. And what they see complicates everything. The Shkval is fast. It is unstoppable. But it has a fatal flaw. The rocket motor and the collapsing bubble generate noise. Immense noise. The telemetry indicates the weapon produces over 200 decibels of broadband sound. To understand this, a commercial jet at takeoff produces about 140 decibels. The Shkval is significantly louder, and sound travels 5 times faster and far more efficiently underwater than in air. The acoustic signature is so intense that it is blinding, or rather, deafening. Conventional torpedoes are hunters. They use sonar to ping a target or listen for the target's engine noise, guiding themselves in for the kill. They can turn, reacquire, and dogleg. The Shkval cannot do this. The weapon's own roar drowns out any return echo. It blinds its own sensors. It is, by design, deaf. This means it cannot use active or passive sonar homing. It cannot listen for the carrier it is trying to kill. Furthermore, the rocket motor's finite burn time means the weapon flies a straight line. It steers, but only to keep itself straight. It cannot perform complex maneuvers. It cannot chase a target that zigs and zags. So, the guidance must be inertial. This means the bearing and depth are programmed before launch. The gyroscope spins up, the submarine calculates the target's position, and the weapon is fired. Once it leaves the tube, it is on its own. It flies the preset path with no feedback from the environment. The prototype launches again at the lake. The acoustic signature is so loud that the recovery divers on the surface vessels can hear the roar through their hull-mounted sensors miles away. It drowns out their own engines. It masks all other sounds in the test corridor. The test director watches the clock. At 200 knots, even a 1-degree error in the initial alignment translates to hundreds of meters of lateral drift by the time the weapon reaches 7 kilometers. If the gyroscope drifts, the weapon misses. The test proves the weapon is accurate enough for a straight shot, but the tactical implication is stark. Shkval cannot be used for covert strikes. There is no such thing as a sneak attack with a rocket-powered torpedo. Any surface group with competent sonar will hear the launch instantly. They will know exactly where it came from. The submarine gives away its position the moment it pulls the trigger. Doctrine officers classify the Shkval not as an offensive hunter, but as a weapon of last resort. It becomes a silver bullet. It is designed to be carried in limited numbers, 1 or 2 per submarine, alongside conventional torpedoes. It is reserved for the nightmare scenario the submarine has been detected. The enemy destroyers are closing in. Stealth is lost. The captain is about to die. In that moment of desperation, he fires the Shkval. He bets that the kinetic speed of the weapon will reach the enemy faster than they can kill him. It is a weapon of panic, of defense, of ensuring that if the submarine goes down, it takes a high-value target with it. The speed that makes it unstoppable also makes it tactically narrow. It is a straight-line sledgehammer in a game of chess. In 1977, the Shkval enters service. It is loaded aboard Soviet nuclear submarines, a secret ace in the hole. For nearly 20 years, it remains a rumor in the West. Intelligence reports speak of high-speed underwater objects, but the details are scarce. Then, the Iron Curtain falls. The Soviet Union collapses. And in the chaos of the 1990s, the secrets begin to leak. In 1995, looking for cash and export customers, Russia does the unthinkable. They publicly reveal the Shkval at an international arms expo in Abu Dhabi. They put the weapon on a stand. They hand out brochures. The announcement ends 2 decades of silence. Western naval intelligence officers flock to the display. They confirm the 200-knot performance through the analysis of the acoustic data they had collected over the years. They immediately begin reverse engineering efforts. The United States, Germany, and China all start their own supercavitation programs. But the Russians are playing a dangerous game. They are marketing the weapon, but they are fiercely guarding the how. The specific composition of the solid fuel, the exact formula of the ablative ceramic, the geometry of the gas injectors, these remain state secrets. In April 2000, the line is crossed. U.S. Navy Captain Edmond Pope is in Moscow. Pope is a retired intelligence officer working as a private defense consultant. He is meeting with former Shkval engineers, men who are now struggling in the post-Soviet economy. Pope is seeking technical data. He wants the blueprints for the rocket motor and the nose cone ablation system. He believes that because the weapon was displayed at an arms show, the technology is fair game. The FSB, the Russian Federal Security Service, disagrees. They have been monitoring all foreign contact with the Shkval team. They have bugged the meetings. Pope is arrested. He is charged with espionage. The case signals to the world that even 23-year-old technology is still considered a strategic asset. Russia is willing to sell the torpedo, but they will not sell the secret of how it works. Pope is convicted in December 2000 and sentenced to 20 years in a labor camp. The diplomatic fallout is immense. 8 months later, President Vladimir Putin pardons him on humanitarian grounds, and Pope returns to the U.S. But the message is clear. The Shkval is not just a product, it is a national treasure. Today, more than 2 decades after that revelation, the legacy of the Shkval remains singular. The United States has tested supercavitating projectiles. China is rumored to be developing them. Germany has built prototypes. But no navy has fielded a fully operational weapon that matches the sustained 200-knot performance of the original Shkval. The trade-offs, the noise, the lack of guidance, the short range, have proven difficult to overcome. Modern navies prefer stealth and precision over raw speed. Yet the Shkval stands as a monument to Cold War engineering. It proved that the impossible could be built. It proved that a torpedo could fly through a bubble. It transformed Professor Logvinovich's 1961 chalkboard sketch into a kinetic reality that rests, heavy and silent, in the torpedo tubes of the Russian fleet to this day. A weapon that waits for the moment when stealth fails, ready to scream through the ocean at the speed of a small airplane.